Hello everybody, welcome to my channel VKS Chem Tutorial. In this video, I will discuss one of the important type of pericyclic reaction, the electrocyclic reaction. An electrocyclic reaction is intramolecular reaction in which a new sigma bond is formed between the terminal carbon of linear conjugated pi system to form a cyclic compound. From the linear conjugated pi system, one double bond disappears and the remaining double bond shift their position. See this example. It is 1,3-butadiene, a linear conjugated pi system. This molecule containing 2 pi bond. In the electrocyclic reaction, it gets converted into cyclobutene with a new sigma bond, and the number of pi electron in this cyclic compound, you can see only 2 pi electrons. From the acyclic linear system, 2 pi electrons are transformed into 2 sigma electrons in the product. So number of pi electrons in the acyclic system is 4, but in the cyclic system it is 2 with a new sigma bond. In the case of this example, it is hexatriene. The linear system is hexatriene, where the number of pi electrons are 6, or there are 3 pi bonds. And during electrocyclic reaction, it gets converted into cyclohexadiene with 1 pi bond less than the acyclic system. And a new sigma bond is formed here. During this conversion, 1 pi bond is lost from the acyclic system and a new sigma bond is formed in the cyclic product. It is the characteristic of an electrocyclic reaction. The forward reaction is called electrocyclic ring closure, while the backward reaction is called electrocyclic ring opening. That means electrocyclic reactions are reversible in nature. Before discussing electrocyclic reactions in detail, we have to know how to construct Huckel molecular orbital diagram for conjugated alkenes, and some terminologies come across in electrocyclic reactions such as con rotation, disrotation, etc. First of all, we have to consider how to construct Huckel molecular orbital diagram for a conjugated alkenes. For constructing Huckel molecular orbital diagram, we have to know these points, such as the number of pi molecular orbital is equal to number of carbon atoms over which the pi electrons are distributed, which is represented as small letter n. Also, the number of nodes in a molecular orbital, which is represented as n minus 1. Odd number of molecular orbital will be symmetric with respect to mirror plane and anti-symmetric with respect to C2 axis of symmetry, while even number of molecular orbital will be anti-symmetric with respect to mirror plane and symmetric with respect to C2 axis. Consider the case of ethylene molecule. It is the Huckel molecular orbital diagram of ethylene. Ethylene containing 2 carbon atom, and hence there are 2 pi molecular orbitals distributed in carbon atoms of ethylene. So ethylene has 2 pi molecular orbital represented as psi1 and psi2. Here psi1 is bonding molecular orbital and psi2 is anti-bonding molecular orbital. Psi1 has n is equal to 1. It is an odd number, so it is symmetric with respect to mirror plane and anti-symmetric with respect to C2 symmetry. See, there is no node in this molecular orbital. The number of node is n minus 1. Here n minus 1 is 0. Then in the case of antibonding molecular orbital psi 2, it is an even number. So the molecular orbital is antisymmetric with respect to mirror plane and symmetric with respect to C2 axis. You can see here is a node represented as vertical dashed line. The number of node is n minus 1. Here it is 2 minus 1. So is equal to 1. And so this anti-bonding molecular orbital psi 2 of ethylene has one node. Then consider the Huckel molecular orbital diagram of butadiene. It is the Huckel molecular orbital diagram of butadiene. Butadiene consists of 4 carbon atoms. These 4 carbon atoms containing one pi molecular orbital or pi molecular orbitals, 4 pi molecular orbitals are distributed on the carbon atoms. So there are 4 pi molecular orbitals, psi 1, psi 2 are bonding molecular orbital, psi 3 and psi 4 are anti-bonding molecular orbital. Psi 1, it is 1 is an odd number, so it is symmetric with respect to mirror plane and anti-symmetric with respect to C2 axis. Psi 2 is this psi 2 molecular orbital, 2 is an even number, so it is anti-symmetric with respect to mirror's plane and is symmetric with respect to C2 axis. 2 minus 1, that is equal to 1, and hence this molecular orbital has a nodal plane which is indicated by this dashed line. And in the case of antibonding molecular orbital, psi 3 is an odd number, so it is symmetric with respect to mirror plane and anti-symmetric with respect to C2 axis. 3 minus 1, that is 2, and so it has 2 nodes. It is indicated by vertical dashed line. Then psi 4, psi 4 is an even number, so it is antisymmetric with respect to mirror plane and symmetric with respect to C2 axis. 4 minus 1, that is the number of node, that is equal to 3. So there are 3 nodal planes indicated by this vertical dashed line. It is the Huckel molecular orbital diagram of butadiene. Okay. Similarly, in the case of 135 hexatriene, there are 6 carbon atoms over which the pi molecular orbitals are distributed. The 6 pi molecular orbitals are represented as psi 1, psi 2, psi 3, which are bonding molecular orbital. Psi 4, psi 5 and psi 6 are anti-bonding molecular orbital. Psi 1 is symmetric with respect to mirror plane and anti-symmetric with respect to C2 axis. Psi 2 will be anti-symmetric with respect to mirror plane and symmetric with respect to C2 axis. Psi 3 is symmetric with respect to mirror plane while anti-symmetric with respect to C2 axis. The antibonding psi 4 molecular orbital, 4 is even number, so it is anti-symmetric with respect to mirror plane and symmetric with respect to C2 axis. Psi 5 is an odd number, symmetric with respect to mirror plane and anti-symmetric with respect to C2 axis. Similarly, psi 6 is anti-symmetric with respect to mirror plane and symmetric with respect to C2 axis. This much about the construction of Huckel molecular orbital of linear conjugated system. Okay, in an electrocyclic reaction, a new sigma bond is making between 2 terminal carbon of a linear polyene to form a cyclic product. It will take place by 2 ways, either by conrotatory process or by disrotatory process. Conrotation. In conrotation of the electrocyclic reaction, both the p atomic orbitals of the terminal atoms turns in the same direction, such as both atomic orbitals rotating clockwise or anti-clockwise. You can see both the p atomic orbital component of the terminal atom turn in the same direction. You can see the arrow pointing same direction, and this type of rotation of atomic orbitals in an electrocyclic reaction is called conrotation. The important stereochemical outcome of the conrotation is the substituent on the terminal of the open chain reactant pointing in the same direction will be cis in the cyclic product. See the substituent here, the substituent B and B in this carbon atom and A in this carbon atom pointing same direction, pointing in the same direction. And these substituents in the cyclic product, you can see these substituents are orienting in the same direction, that is cis to each other. Here you can see B and A are on the same side of the chain, cyclic or ring on the same side, and hence it is cis product. That is one of the important stereochemical outcome of conrotatory process. Okay, similarly, when both the p atomic orbitals of the terminal atoms turn in the opposite direction in such a way that one atomic orbital turns clockwise and the other anti-clockwise, it is called disrotation. See here the terminal carbon atom, see the terminal carbon atom, the atomic orbitals of the terminal carbon atom turns in the opposite direction. One atomic orbital turns clockwise while the other turns anti-clockwise. And this process of rotation is called disrotation. The important stereochemical outcome of the disrotation is substituent on the terminal of the open chain reactant pointing in the same direction. Here see B and A are pointing in the same direction, will be trans in the cyclic product. You can see this B and A of the terminal carbon atom of the acyclic reactant is orienting in the opposite direction or trans to each other in the cyclic product. That is the stereochemical outcome of the disrotation. Okay, then derivation of Woodward-Hoffmann selection rule for electrocyclic reaction. There are several methods for derivation of Woodward and Hoffmann selection rule for electrocyclic reaction, such as frontier molecular orbital method, correlation diagram method, Huckel-Mobius analysis, etc. Among these, first of all, we will discuss the frontier molecular orbital method in this video. See, derivation of selection rule needs consideration of only HOMO, highest occupied molecular orbital of acyclic conjugated system for electrocyclic reaction. We are considering HOMO in the ground state in order to examine whether this reaction taking place thermally by either of the rotation, conrotation or disrotation. And we are taking into consideration of HOMO in the excited state for whether a photochemical reaction takes place either thermally or photochemically. That means, we are taking into consideration of HOMO of excited state of a cyclic conjugated system to determine whether this reaction taking place photochemically, either via conrotation or disrotation. First of all, we will take into consideration of this acyclic conjugated system, that is butadiene. On heating, ring closure takes place to form cyclobutene. Here we are considering the HOMO in the ground state of butadiene, that is site 2. Here n is equal to 2, an even number. So site 2 orbital is antisymmetric with respect to mirror plane and symmetric with respect to C2 axis. See, it is the site 2 molecular orbital. The atomic orbital or p atomic orbital of the terminal carbon atom rotate on the same direction. See, it is the con rotation, whereby the positive lobes you can see of the terminal carbon atoms will coincide in order to have the maximum overlap, whereby bonding interaction takes place to form the cyclic product, cyclobutene. And so we can say the thermal interconversion of butadiene to cyclobutene via conrotatory process is symmetry allowed process. If we excite or if we irradiate the butadiene system by light, electrons will be excited from the site 2 molecular orbital to the site 3 molecular orbital. Now the HOMO will be site 3. N is equal to 3. It is an odd number. Thereby site 3 molecular orbital will be symmetric with respect to mirror plane and antisymmetric with respect to C2 axis. It is the molecular orbital site 3. You can see similar lobes will coincide in order to have the maximum overlap only via disrotation. Here this p orbital rotate this direction and this p orbital of the carbon atom rotates the opposite direction, whereby these positive lobes of the terminal atomic orbitals of the terminal carbon atom, the same lobes of the terminal, the atomic orbital coincide in order to have the maximum overlap. This is done by disrotation or rotation in opposite directions. Thereby, we can say in presence of light or photochemical interconversion of butadiene to cyclobutene take place via disrotation, that is frontier molecular orbital method. Okay. Similarly, we can take the 4n plus 2 pi system in order to derive Woodward-Hoffmann's theory by FMO method. For example, the thermal interconversion of hexatriene to cyclohexadiene. See, the acyclic system is a 4n plus 2 pi system. There are 6 pi electrons distributed on the 6 carbon atoms. Therefore, there are 6 pi molecular orbitals. Among these, 3 molecular orbitals are bonding. The remaining 3 are anti-bonding. The 6 pi electrons are distributed 2 each in the 3 bonding molecular orbitals. Thereby, in the ground state, the HOMO is the 3rd bonding molecular orbital, that is site 3. 3 is an odd number. Thereby, this molecular orbital is symmetric with respect to mirror symmetry and antisymmetric with respect to C2 axis of symmetry. Then see the molecular orbital picture of site 3 molecular orbital. You can see the terminal atomic orbitals or atomic orbitals on the terminal carbon atom, the atomic orbitals on the terminal carbon atom will move or rotate in opposite direction in order to have the similar lobes align in the same direction to have the maximum overlap between them. Thereby ring closure takes place. So only disrotation will be allowed for the maximum atomic orbital overlap in order for the ring closure. And so we can say thermal interconversion of hexatriene to cyclohexadiene is a disrotatory process. Then if we excite or irradiate the molecule hexatriene, one of the electron from site 3 molecular orbital gets excited into site 4 molecular orbital. Now the site 4 molecular orbital will be the HOMO after irradiation of the molecule. Then 4 is an even number. So this molecular orbital will be antisymmetric with respect to mirror plane and symmetric with respect to C2 axis. And if we represent the molecular orbital site 4, you can see atomic orbital overlap will take place only when the atomic orbitals in the terminal carbon atom rotate in the same direction, either clockwise or anti-clockwise. Therefore, we can say the photochemical interconversion of hexatriene to cyclohexadiene is a con-rotatory process. Okay, now we can summarize the Woodward-Hoffmann selection rule for electrocyclic reaction. For an foreign pi system, the thermal interconversion is a con-rotatory process, whereas the photochemical interconversion is a disrotatory process. Whereas for a foreign plus 2 pi system, the thermal interconversion is a disrotatory process, whereas the photochemical interconversion is a con-rotatory process. Okay, I have already discussed what are electrocyclic reactions, what are or how to construct Huckel molecular orbital diagram, and what are the con-rotatory and disrotatory process, and how to analyze an electrocyclic reaction by Woodward-Hoffmann selection rule with FMO method or by FMO method, frontier molecular orbital method. We have considered the FMO method for analyzing the thermal and photochemical interconversion of butadiene to cyclobutene and also hexatriene to cyclohexadiene. With this discussion, I conclude this video. Thank you for watching. Thank you.